Welcome, everyone. Thank you for attending this today's talk. I see there's quite a few folk that attended yesterday's talk as well, which is great. Thanks for coming back. I'm glad at least we didn't push you away. At the very least, I hope we could whet your curiosity to learning more about TypeDB, especially comparing it to property graphs, which are particularly popular these days. So let's start. So what we're going to start is just with a general introduction, why we're doing this talk in the first place, why we think it's helpful. We're going to then look at the challenges of working with a graph database. We're going to look at how to model and define schema and compare how those two approaches are different in a property graphs and in TypeDB. We're going to look at how to read data, and finally we're going to look at automated reasoning and effectively what that means to a database and to in TypeDB and in a property graph. So now, graphs have been around for a long time. I'm going to assume a general familiarity with graph databases for this talk, but in graph theory as the basis of a graph database has been around for a long time, where structure, meaning is very important as a subfield within mathematics, and it was only quite recently with especially Neo4j paving the way to actually use that as the basis of an actual commercially and open source sustainable database. But of course, some of these approaches have been around for a long time in terms of both in terms of maths and graph approaches. This trend is perhaps a little bit outdated already, but I think it's fair to say for anyone that's listening to this talk that the graph databases in general are hot at the moment. Many people are turning their heads around to actually learn about them and understand the value that they may bring to our software. So the key thing that we hope to show today when it comes to comparing TypeDB with a graph database is that the core tenet of how the software TypeDB differs to a graph is in TypeDB's type system. And TypeDB's type system we can organize as having the expressivity that it gives the user, the safety, the inference, and the optimization that it provides. And the way that's provided is effectively by providing a higher level language, a higher level abstraction over a graph database. And so as we go about through this talk, I think and we'll get into this section right now, when we think of a graph database, and when we think of TypeDB, we should really think of an abstraction of a graph database. In the literal sense, the way TypeDB is built is actually with its own graph engine. We ourselves build our own graph engine to actually build on top of that the abstraction layer with the type system that TypeDB offers. And the reason we did that is because when we started the company 6 years ago, and to date, there's actually a lot of challenges when working with a graph database. So what's wrong with graphs? So the first thing is that, contrary to perhaps what some people may think, modeling complex data, especially very semantically rich data, is actually very difficult in graphs. Not everything fits into vertices and edges, especially if you're forced into having a unidirectional edge connecting two nodes. It's also very difficult to maintain consistency of data. Most graphs don't actually implement an actual schema constraints at the database level. And then all of that together made writing graph queries actually very difficult when it comes to actually translating a higher level question to the database because of the safety lacking in the structure, because of lack of schema constraints, and because of the model not actually being able to represent a conceptual model true to its form. So what we consider is that graph databases are actually too low level to handle complex data and handle software and the type of data that software today needs to use. And by the way, just as a side note, if you're posting in the chat, please hit to all panelists and attendees. Otherwise, only Daniel and I can see your message. And perfectly fine to private message you, but we'd like to get a bit of a sense of who's here, because most people they click on the all panelists message, and then only us can see your message. So I would advise you just to take note of that. So now, to compare both approaches beyond just the philosophical and the conceptual model on how both the databases work, we also want to look at actually how do both implementations differ, specifically from a modeling point of view and how we define schema. And the way we want to go about doing that is actually by looking at examples. We found that to be the helpful way of how to actually go about doing so. Now, I spoke before about TypeDB being an abstraction layer over a graph model. And that's, in the truest of sense of words, that's really how TypeDB should be considered. And the higher level expressivity and everything that TypeDB offers in addition to a graph is captured in the type system that TypeDB offers, hence the name being also TypeDB. Now, if we consider the graph model to be fundamentally based on nodes, relationships, or edges, and properties, the TypeDB model is actually based on an entity relationship model. And that's something very important to keep in mind. The entity relationship model, as actually originally espoused by Chen in 75, is what TypeDB actually implements as its data model. So normally, if we start with some sort of ER diagram, we would normalize our data to get to some sort of graph model or tables. The point that we're saying with TypeDB is that instead of thinking of it in terms of having to normalize our data, the conceptual model is actually the model how it works in the database. So that means we model as first-class citizens, we have entities, relations, and attributes. And then we have the concept of a role. And the concept of a role is effectively how we contextualize something, a relation, an attribute, or an entity, as playing a role inside another relation. Now, because those concepts, all of those are first-class citizens in the model, what that means is that we can have attributes. We can have relations connected to other relations. And there's a lot of very cool ways of modeling our data that we may not have considered at the start that now TypeDB provides us. And finally, then we've got the notion of rules, which enables us to do rule-based reasoning at the database layer during query runtime. So, what we say here is that TypeDB abstracts away the graph model. So everything fundamentally from a modeling perspective that you can do in a graph, you can do in TypeDB. And in addition to that, we offer more functionalities in a higher level language, in effect. So let's look at an example here. So let's say we have Mary. Mary married Peter on the 2nd of February, 2020. You see how the example, by the way, takes into account European and American spelling? That was not on purpose, by the way. That was not on purpose. But because of the date and the month that are replaced in the Europeans and American spelling. So just before the pandemic, Mary married Peter. Great. I hope they're still together. So how would we represent that in a graph database? So, well, we would consider a person node with the name Mary, another person node with the name Peter. May have an edge between them, married to. So Mary here is married to Peter. Now, the way we would go about doing that in TypeDB is by saying, actually, instead of thinking as nodes and edges and properties, the nomenclature that we would use in the model is actually to say that there's an entity type, person, that has an attribute of type name with value Mary. There's another entity type, person, with the attribute of type name and value Peter. And then there's a marriage relation that connects both of those entities, where both entities play the role of spouse in that marriage. And then finally, there's an attribute of type date on the marriage itself, and that denotes the date on which the marriage happened. So instead of using nodes and edges, TypeDB implements a concept level entity relationship model, which in this example looks effectively the same, but the implications that this has downstream are enormous. Because one of the ways that this enables us is the ability to perform or to model hyperrelations. In a property graph, an edge is just a pair of vertices, whereas a hyperedge is a set of vertices. And the ability to model hyperedges or hyperrelations, as we would call them, it becomes very, very powerful. One example is that of the ability to model ternary relations, where we've got three role players in one. So let's say we've got a supplying relation between two companies. One is the buyer, one is the seller, and we've got one part that's being supplied. So that supplying relation is now represented as just one relation. If we wanted to do the same in, let's say, in a graph, we would end up reifying our graph because we cannot have an edge that connects to three things at once. We would effectively, out of that edge, we would reify it, and we would say, okay, now it's not an edge anymore, now it's a node. And now we can have that supplying relation or that supplying node that connects those three things in one. But this is very, very problematic because now we've reified the graph, we've messed up our model. And so yes, we end up reifying the graph to represent the relation as a node, and that's not good because that's not the model that we actually want to create. And the schema that we would write in TypeDB would look like this. And again, there's no way to do real schema constraints at the database level in TypeDB, whereas in most graph databases. Whereas in TypeDB natively, one of the key benefits of using TypeDB is the ability to model these schema constraints. Because what we're saying here is that in a company entity, a company can play the role of supplier and buyer in a supplying relation, which we define here, and the parts entity can play the role of supplied in a supplying relation. And the supplying relation itself has three different role players that can be attached to it: a supplier, a buyer, and a supplied. And then the actual data pattern or how we would represent it would be like so. This node here that we've effectively reified, the supplying node, is the one that we now can actually say, okay, this connects three things in one node, mimicking the same hyperrelation that you see on the right. Because this supplying relation right here, where this company that we declare as being the variable supplier plays the role of supplier, the part plays the role of supplied, and the buyer plays the role of buyer in a supplying relation. Now, because relations are first-class modeling constructs, we can also have relations refer to other relations, and that allows us to model nested relations. So nested relations could be something like this, where let's say we've got a marriage between two people, a marriage between whoever, and we want to say that the marriage happened somewhere. So we want to say that the marriage happened in a city, and we want to represent that location through a located relation. So we want to be able to say that there's a city that's in which a marriage relation takes place in, and that marriage is connected to that city through a located relation. Now, again, we can't natively do that in a property graph simply because we cannot effectively have an edge point to another edge. So instead, what we end up possibly doing is reifying the graph again, and out of that marriage relation, making a node. So again, we end up reifying the graph to represent the relation as a node. And really, we shouldn't be reifying our graph. We want to be able to natively have a data model that can actually represent the domain that we're trying to model. And so here you see how we effectively allow this marriage relation to play this role of locating in this located relation that is defined down below. This located relation refers to this locating role player, and that allows us to declare that indeed a marriage can play the role of locating in a located relation. And then the query pattern itself would look something like this. What we do in TypeDB, and we compare Cypher here, of course. In TypeDB, we've got a marriage relation, which we can assign that marriage relation to a variable. So that variable name here is called marriage. And by assigning that marriage relation to this relation, we can now actually put it in another relation, in this case, a located relation. So again, by assigning variables to relations, we can now do very cool things with them. Now, the next section that we want to discuss is the ability to model type hierarchies. So in a type hierarchy can be, for example, let's say we've got a vehicle that we can subdivide into having as cars, as aircrafts, as trucks, and then we can again subdivide those into fixed wing aircraft, jet aircraft, garbage truck, heavy trucks, and we want to be able to capture that also at the database. So out of the box, within the modeling language, TypeDB supports the ability to model type hierarchies, specifically single type hierarchies. So here we've modeled in the TypeDB schema, we've modeled we've modeled effectively a vehicle type hierarchy with aircraft, with cars, with trucks, and all of their relevant respective subtypes. Now, how would we then insert type hierarchies? So one approach that we could do is to, at least in Cypher, is to add multiple labels to a node. So here, for example, we can say that Suzuki, which is of type minivan, is also as a label car and vehicle. So by adding multiple labels, that's one way of how we can effectively model the ability to create type hierarchies. So, and of course, in TypeDB, we don't have to do that. We would simply declare something as a minivan, and then that would allow us, that would imply that it's also a car and a vehicle. But now, and this becomes interesting, now what we have is that, let's say we want to fetch all vehicles. So now if we've correctly assigned all the labels, we could quite easily in Cypher just simply ask for the vehicle label. That would be fairly simple query, and also it will be fairly simple in TypeDB. The difficulty now is that because our data is invalidated, this Cypher query is actually very unsafe, because we don't know if actually people have labeled all of the data correctly that has been ingested, given the lack of schema constraints. So if you want that safety, you unfortunately would have to literally declare every single type that you want to query in order to actually get all the vehicles, if you want to be sure that your query is safe. So in Cypher, we would be forced to decide between a long query with certainty or a short version without. Now, type hierarchies can also be made for relations. So here we've got a relation type hierarchy, an employment relation that has two subtypes. It has a full-time relation, employment relation, and a part-time employment relation. We can model that in TypeDB, again, as we would with an entity type, by using the keyword sub and saying that a part-time and a full-time employment are subtypes of the employment relation. Now, if we're now fetching for all persons that are in an employment relation, unfortunately, in an edge, we can't have multiple labels in Cypher, so we would have to use effectively, well, specifically query for all the types that we want to be returned in Cypher, whereas in TypeDB, we can quite easily just simply ask for the employment relation. That would then imply that we're also meaning all the subtypes. So the part-time employments and the full-time employments. So let's look now at how do we read data. So let's say we're asking, who are Susan and Bob's common friends? So a Cypher query can look like something like this, where we've got a person who knows another person. Bob knows Susan, and Bob also knows this friend. So, and now we want to be, now effectively want to be returned this common friend. In TypeDB, we would do something like this, where we first declare Bob, Susan, and this friend, which we don't filter for. And we simply then ask, give me, so Bob and Susan are friends. Susan is connected to this friend. And then we want to make sure that we want to fetch the friend, just as we ask using the return keyword, because the friend is both connected to Bob and the friend is connected to Susan. and in case it wasn't clear, the variable, the dollar sign denotes the fact that that it is a variable effectively. So Gregory, to your question, can a single relation type have varying number of entities? If your question is whether, for example, in this relation right here, we can have n number of things play a role in a relation, the answer is yes. And that's because of the hyper graph, the hyper relation under the hood. So, and I say things, by the way, because it doesn't just need to be entities. I could, for example, declare this attribute to a variable. And if I do that, I can actually also put it in this relation if you have allowed that in your schema, right? So you need to make sure that it first is defined like so in your schema. And then you can put any relation, any attribute, and any entity in a relation. And you can have 6 entities and 2 attributes. I'm making this up right now. You can have, whatever you like number of role players in one relation. You can have 100. There's no limit necessarily. The limit may be theoretical or on how it's implemented under the hood. But you can have n number of things play a role in a relation. So let's look at a slightly more complex question here. So let's say we're asking which movies have been released after 2002 in the Odeon cinema by Pixar. So, well, this is the Decipher query, where you were using a where filter here to make sure that the years of movies are after 2002, and then we've got the query pattern at the top. The equivalent in TypeDB would look like so. So first, and by the way, the ordering doesn't actually matter. It's just easier in terms of readability to split out the entities and the relations, but by no means is there any functional difference. So here what we're saying is that there's a cinema, there's a city, there's a studio, and there's a movie. The movie has a title, and the value of that title is what we want to return. So we assign it a variable name. So that variable name now is something that we can fetch for later. Now, then I say that London is connected to the cinema. So the cinema is located in London. The cinema is releasing a movie, and that movie is producing, or that studio is producing that movie with, and that production, so that year, that production relation has an attribute of type year, where the value is assigned to this variable name. And then this variable, we just say that the value of that variable must be over 2002 to say that it must be after the year 2002. And so that would be the way we would do it in TypeDB. And then the way we would think of this query in terms of conceptually would be, again, thinking what are the entities, what are the relations, what are the attributes? And in the nomenclature that we use, we have entities denoted as rectangles, relations as diamonds, and attributes as circles. So finally, something that is a bit difficult to compare actually, because natively graph databases don't actually support automated reasoning, so at least not property graphs. So the comparing TypeDB to a graph becomes difficult, because it's a bit unfair to compare something that TypeDB has versus something that a property graphs simply is unable to do. But still, to show effectively the benefits of where rule-based and type-based inferencing comes into play, is there's a couple examples where we can see. So first, let's take this question here. Return all siblings of a person, of a family, for example. So we may want to say that there may be people that have sibling relations with their siblings, but maybe there's other people that don't have direct sibling relations with each other. And instead, we want to mimic, we want to say that also give me everyone who has a parent, and then also if that parent has other children, give me those children and those connections, because they will be siblings. Now that can be represented in a rule with TypeDB, where we can effectively infer that siblingship relation simply by creating a relation, a rule that infers a relation based on saying that if a child shares the same parents with another child, well, then those children must be siblings. And that rule can be represented using, first, again, as part of the schema, we write the rule. We first have the when part of the rules that defines the conditions of the rule. So here in this case, we say that if a parent has a child, and if that parent has another child that are not the same, we then want to create a relation between child 1 and child 2. And now we can look at another example. Let's say we've built a model where we only have created parent relations. So we only have edges that show I am the parent of this person. Daniel is the parent of his dog. Not really, but he likes to think so. That's a recurrent joke here, by the way. I'm sorry, Daniel. I'm really sorry. So let's say we only have parent relations. How can we fetch that someone is a cousin of someone? Well, we can do that by actually going all the way to the grandparent, because if I am the son of someone and that parent is the child of someone else, then if there's another child that has another child, then we will be cousins. So now we could infer that cousinship relation. We've made this up for the purpose of this example here, but we could infer a cousinship relation using 2 rules. The first rule can infer the cousinship relation between the child and the nephew. And we can do that like so. Here we simply say that if a parent is connected to a child, if that parent is connected to someone that we call here nephew, then the child and the nephew are cousins. Now, the cool thing here is that what if one of the conditions is actually also inferred? This is where it gets really interesting, the reasoning. Because what if one of those relations is actually inferred? Now, we can infer this onship relation also. Here, what we say is that if a person of gender female, if that person has is the child of a parent, and if that parent has a sibling, then that sibling and that child are in an onship relation, where someone plays the aunt and someone plays the niece. The point being is that we can use multiple rules that are chained together to effectively exponentially grow our data set and increase the amount of knowledge that we have available. Now, of course, we can also represent more complex business logics in rules. So for example, what schedules overlap? We could potentially create an inference that infers an overlaps relation that encapsulates the text if 2 specific schedules with an end time and a start date overlap. We want to connect them through the overlaps relation here in the rule. And if we want to take it to an even more interesting example where the reasoning becomes even more interesting, this is an example or adapted one from a real use case. If we're looking for the disease risk factors that someone, for example, John Doe may have, we could actually write this in just a couple of lines of code in TidyDB. And again, it's not necessarily about comparing the lines of code here, but is looking at the logic here that would define what a disease risk factor would be, will have to be encapsulated in the actual query that we're writing, in this case here in Cypher on the left here, versus in TidyDB where the logic is actually encapsulated as part of the schema. And when you're querying for your data, in this case, you're just querying for the risk factor relation. Because the difference here is the number of important operations we can perform without thinking about them. Simply because when you're querying for the risk factors, you may not necessarily know all the underlying logic that defines if someone has a risk factor. So let's say for this example, let's say if we said that if a person consumes more than 10 units of alcohol per week, then they are at risk of diabetes 2 and hypoglycemia. And let's say if a person consumes more than 12 cigarettes per week, then they are at risk of multiple sclerosis, high blood pressure, COPD, high cholesterol, and heart disease. And if someone's parent has been diagnosed with diabetes 2 and or arthritis, then they are at risk of those diseases as well. Now, that rule, that each one of those statements can be written as its own rule. For each one, we infer a particular risk factor. And in fact, we actually can create a hierarchy here as well of risk factor diseases, of risk factor relations. Here we've got a smoking risk factor, and then we've got a hereditary risk factor, and they all can be subtypes of their parent risk factor, which is the one that we can then query for in the actual query. So to take a step back a little bit and at least catch my breath a little bit, the key tenets of TypeDB's type system surround themselves around the expressivity. So the expressivity is rooted in the type system, in the entity relationship model, the ability to represent hyperrelations, to represent nested relations. The second is the safety, and that's what we saw in terms of schema constraints. And the safety is also represented in the data we can query. If you, for example, if you write a query that doesn't satisfy the schema, you're going to get an exception rather than just an empty set, as opposed and to actually tell you that, hey, your query is actually wrong. We've looked at the inference. The inference allows us to create effectively logical abstractions of certain patterns. And the optimization is something we haven't looked at today, but because of the type system, we can actually increase the performance of queries that are run because of all the type information that is embedded for the query planner. So now, the main point I hope to have shown today is that when we think of TypeDB, and that's something that we hope to show, is that ultimately TypeDB is an abstraction layer over a graph database. So when we consider TypeDB in relation to graphs, it's important to keep that in mind, because a graph database is, at the end of the day, quite a different technology than TypeDB. So with that in mind, I thank you very much for your attention. I think we have a few questions, Daniel.
Indeed, bravo, Tomas, as always, well done. There are a couple questions. Just going back to Stefan's first, how might we constrain a relation so that there are only, let's say, 2 persons in a marriage?
Great question. So certain cardinality constraints, we actually haven't provided those as features just yet. So we can't yet specify that only 2, for example, only 2 people can be in a marriage. Those safety constraints we haven't added yet, but those are certainly ones that we'll be adding soon.
Yeah. And Gabrielle asks, when you define a rule, does some process kick off to map out all the consequences, or does that happen at query time? I.e., does changing or defining a new rule cause a lot of computation, or does that only happen when a rule is needed in a query? And Stefan maybe takes a stab at it and says it should be at definition time, otherwise you could not subclass it.
The rules only get triggered at query runtime. So first, before you commit a rule, there will be a check that checks whether the rule is actually satisfiable or not, whether it adheres to the schema, whether it actually logically makes sense. But the actual result of the rule, the rule actually will only trigger when you query for something that's in the conclusion of the rule. So specifically, the way the reasoner works, so we implement something called backward chaining, and backward chaining basically means that if you have a query that you ask the database, and that query contains a type that is contained in the conclusion of a query, then of a conclusion of a rule, then the reasoner will just look at those rules that are relevant to that query and ignore all the other rules. Then it will check the conditions of that rule and check also, are any of those conditions participating in any other rules, and effectively backward chain until it satisfies and resolves the query and gives you an answer. So that's why the rules only get triggered at query runtime.
Good question. And so this is, again, the moment where you can raise your hand and jump off mute, and I can and we can share feedback, questions, ideas, whatever you'd like with the rest of the group. Otherwise, Discord, again, is a great place to drop questions as you begin to digest the presentation and so forth. This will obviously be on YouTube following, and we'll send that link out to everybody. Okay, go ahead.
No, I should also add, if anyone wants to share what they're building with TidyDB, I guess now is a better time than any to do that. If you're looking to share some of the work that you're doing and see and collaborate with other people in the community, feel free to jump on the mic, and Daniel
Absolutely.
and I will be happy to listen.
Yeah, this is, this is sort of like the emulating the live meetup experience with the open mic at the end of the event. So we try and do that here, where you can come off mute and share with the rest of the group. We would love to hear if you're working on something right now, and let you share that with the wider group. And again, Discord is a great place to find other collaborators, find folks that might contribute to projects. Encourage that. So if there are no more questions,
Not everyone at the same time.
I was going to say, not everybody at the same time. And for those in the room that maybe are graph database enthusiasts, we would love to hear your thoughts after hearing the talk. So please feel free to share those. But again, we know that this can be a lot to digest all in one sitting. So feel free to process and then come back and let us know what you think. We would love to, I know the community would love to hear it.
Good.
All right. Oh, here we go. Gabrielle, hello.
Hello, can you hear me? Hello, hello.
Hello, hello.
Hey, Gabriel.
Thank you both for a really nice talk. And thanks for putting all this material online. I was reviewing some of it. This might be a slightly technical question, I'm not sure, but it was something that was confusing me a bit. I've seen a lot of schemas that define attributes using something called owns. And so say company owns name and person owns name, right?
Yeah.
Both can have names. Does that mean that, does that cause any conflict? Or it was confusing to me a little bit. Does owns mean this thing can only belong to one entity type? Or does it just mean that name is always a string and both of those things can have a string name?
The keyword owns is simply the keyword to declare that a attribute can be owned by a certain type. So a relation can own an attribute. So, relation owns name, attribute can even own an attribute. The keyword owns is only used in the schema, the definition. So that it's just a keyword really to say that if you have a person entity, and then let's say you've got a name attribute, an attribute of type name, and you want to allow a person type to have a name, you simply say person sub entity owns name. That doesn't mean that now if you have another entity called organization, that organization can still own a name as well. So it's just a keyword to define that something owns a particular attribute. But again, it doesn't limit the number of entities that can have the attributes.
Okay.
Yeah. Yeah. Does that make sense?
Name can be defined separately as an attribute, and then it can be attached to multiple entities.
Yes.
Okay.
Yes. To everything after that. But bear in mind the way the attributes work in TidyDB is that if you've got an attribute of type name with value, John, let's say there's 1,000 Johns in your database, you're going to have 1,000 entities of instances of John that have the name John, but the actual attribute with value John will only exist once, but that will refer to all of those ones. So if there's a value that's the same, that will only exist once in the database. Does that make sense?
Okay, so that's a storage optimization feature in some sense.
And also just philosophically, for us, like the attribute age 18 only exists once.
Mm-hmm.
You see what I'm saying? It's not like you have a table and you've got, a lot of 18s.
Mm-hmm.
So it's also a philosophical way of thinking.
Okay, thank you. That makes sense.
Thank you for coming off.
Thank you, Gabrielle.
For sharing, Gabrielle. Much appreciated.